Good day everyone, it's me again, Mabel Amlola from BSCE Section R, and I'm going to report to you the plate number 2B. So, we got here a 600 mm and a 350 mm reinforced concrete beam with a double layer of steel bars. The clear spacing between the layers as per ACI has a standard distance for 1 inch in spacing. So we have given 24 MPa or 3045.7 in PSI for the FC prime and 420 MPa or 60,915.8 in PSI or 61 in KSI for the value of Fy. So let's start by constructing the stress strain diagram. So here's our strain diagram. You notice that we have two different strain in diagram. So here's the first strain, which is the epsilon sub t, which is the strain in the steel at the tensile layer of the beam. The second strain is the epsilon s, which is the strain in the steel at the center of this group of steel at the bottom of the beam. The reason why I distinguish these two strains is because epsilon t is used to determine the section as tension control. As per ACI, we need to check the strain in the steel at the extreme layer of steel in tension. So, ACI denotes the distance from the compression fiber to the extreme layer of steel as dt, that is 1. And the distance from the compression fiber to the centroid of our group of steel is this one, letter D. C once again is the depth from our extreme compression fiber to the neutral axis of our section beam, which is this one. Now, at the stress diagram, we've got our compression force acting at depth A. This one, compression force. And we've got tension force, which is equal to the area, this one, area of steel at the bottom layer of the beam times the stress of the steel of the beam. By just simply analyzing the diagram, we can have the value of D as 495 mm or 19.5 inches and the value of D sub T as 530 mm or 20.9 inches. Next, we will now use equilibrium to solve for A, which is the depth of the Whitney stress block. From the rule of equilibrium, the compression force must equal to tension force. From per ACI, the compression would be equal to 0.85 multiplied by FC prime, which is 3045.7 psi, multiplied by the width of the beam, which is 23.622 times A. Substituting our values in, and we have the value of compression, which is 61,155.5 psi times A. And for the tension, which is equals to Fs, the stress in the steel, multiplied by the As. We make an assumption that the steel yields and will later confirm it if does. We have the value of tension force as 365,494.8 pounds. This equation can now solve for the value of A, which is 5.98 inches. Now that the depth of the stress block is obtained, we can calculate C, the depth of the neutral axis. First, we need to figure out the value of C using the ACI code 318 section 10.2.7.1, where A is equals to beta 1 times C. Beta 1 here is a factor that relates the depth of the Whitney stress block to the depth of the neutral axis based on the concrete strength. It is defined in 10.2.7.3. So we have here the formula for beta 1, which is equals to 0.65 less than or equals to 0.85 minus the quantity of Fc prime minus 4,000 psi divided by 1,000 multiplied by 0.05 less than or equals to 0.85. Substituting the values, now we have the value of beta 1 as 0.90. Now that we have the value of beta 1, we can now solve for C, which is this. And the formula for the C is equals to A divided by beta 1. And it resulted to be as 6.64 inches. With C, we can calculate the strain in the extreme tensile steel using similar triangles. With the strain calculated, we can check our assumption that steel yields and determine if the section is in tension controlled. We already have the value of dt, which is equals to 20.9 in inches. So to determine the value of epsilon sub t, we have here the formula, which is C divided by epsilon c equals to d sub t divided by the quantity of epsilon c plus epsilon t. So rearranging the formula or the equation to solve epsilon sub t, substituting our values also, we have the value of epsilon t, which is equals to 0.006. So this means that the section is in tension controlled, and as per ACI section 10.3.4, a beam is considered tension controlled if the strain in the extreme tension steel is greater than 0.005, and it resulted here that our epsilon t is greater than 0.005, which is 0.006. The strain for our section is between the limit for compression controlled 0.002 per ACI section 10.3.3 and the limit for tension controlled sections is 0.005. So therefore, we must interpolate to determine the phi factor in accordance with ACI 9.3.2.2. So to interpolate, we got here the 0.9 minus 0.65 divided by the quantity of 0.005 minus 0.002 equals to phi factor, which is phi factor minus 0.65 divided by 0.006 minus 0.002. So 0.9 here is the phi factor for the tension controlled region. 0.65 is the phi factor for compression controlled section. 0.005 also is the strength in limit for tension controlled section, and 0.002 is the strength in limit for compression controlled section. So by substituting the values again and rearranging the formula, we have here the value of phi, which is 0.98. So Next is we have to determine the strain at which the steel yields and check our assumption that the steel is indeed yielded. So using Young's modulus, so this one, we figured out in which the strain yields and come up as 0.00210 value. So when we checked if the section was tension control, we checked the strain at the extreme layer of steel. So we must calculate this one. We must calculate the strain at the center of the tensile steel to determine if it is yields. Epsilon S is what we need to calculate for. So we have here the formula of epsilon S, which is equals to D multiplied by epsilon C divided by C minus the epsilon C, and substituting the values we come up the value of the epsilon S, which is equals to 0.0058. So we figured out that our value of epsilon S is 0.0058, which is greater than 0.00210. So our assumptions are correct and steel thus yielded. Next, let's determine if the beam section satisfy the minimum steel requirements of ACI. As per ACI section 10.5.1, the minimum steel requirement is this. We can obtain the minimum steel requirement by using this formula or equation. We have here the formula of AS mean, which equals to 3 multiplied by square root of FC prime divided by Fy times B times D greater than or equals to 200 divided by Fy times B times D. So substituting the value, we have the minimum requirement of steel of 0.73 inches squared. To know the area of the steel, we have here the number of bars in our beam times its diameter, and it is said that the diameter of the number 25 bar is equals to 1 inches. So we have here AS, which is equals to 6 times 1, which is equals to 6 inches squared, where it is greater than 0.73 inches squared. Therefore, we satisfy the minimum requirement of steel. Finally, let's calculate the nominal moment capacity of the section. So to make it easier to solve, I prefer to calculate the moment about the center of the compressive force. So we have the design moment capacity, which is equals to phi times T times the quantity of D minus the A divided by 2. So substituting the values as we previously calculated, we have here the value of phi is equals to 0.98 multiplied by the tension, which is the Fs, or the area of steel, multiplied by Fs or Fy, which is 6.00 times 61 ksi, then multiplied again by the D, which is 19.5 minus 5.98 divided by 2. So we come up the nominal moment capacity of 5,921.8 kip inch, or 493.48 kips feet. So this is now our final answer. So I hope you understand and learn from my discussion. Thank you for sparing time on listening to me. God bless us all. Finally, let's calculate the nominal moment capacity of the section. So to make it easier to solve, I prefer to calculate the moment about the center of the compressive force. So we have the design moment capacity, which is equals to phi times t times the quantity of d minus the a divided by 2. So substituting the values as we previously calculated, we have here the value of phi is equals to 0.98 multiplied by the tension, which is the Fs, or the area of steel, multiplied by Fs or Fy, which is 6.00 times 61 ksi, then multiplied again by the d, which is 19.5 minus 5.98 divided by 2. So we come up the nominal moment capacity of 5,921.8 kip inch, or 493.48 kips feet. So this is now our final answer. So I hope you understand and learn from my discussion. Thank you for sparing time on listening to me. God bless us all.